Hello everyone. My name is Shabani Chomv and welcome to solving session. Today we are going to solve some questions that appeared in Advanced Certificate of Secondary Education Examination, uh, paper 2, question number 3, the topic of vector. So welcome. In the year 2025, the question of vector was brought and it contained the three cases, A, B, and C. And now let's see case A. Suppose this is vector P now equals to Ti plus T squared J plus 2Tk. So this is vector of three dimension, the vector of three dimension. Vector of two dimension, normally we have unit I and J, but for here we have I, J, and K. If you see that one, it means that is vector of three dimension. And normally when you graph it on the XY plane, it is always graphed on X, Y, Z plane, X, Y, Z. So this will represent the unit I, J, and this will represent the unity vector K. Now, so you are given vector P and Q, as you can see them, with these coefficients. And now what we are told now here, we find the derivative of the dot product of these given vectors P and Q. Now with respect to T, it means when we change this vector from this unit form into position vector form where we can see x, y, z, it means now that x, y, z, the values will contain t. That's why we are told to find the derivative of the dot product with respect to t. It means after finding this dot product, we will get an expression that will have that t, will have t. And now it will be easy now to differentiate because the concept of derivative, it means that is differentiation. So how to do it? Now let's see case C, case A. So given now, it's a vector P. Now maybe I can write it in matrix form. Here we can write T, then here we have T square, and here we have 2T. And also we are given this vector Q. Now in matrix form, it looks like 1 plus T square, then 2 minus T, then here we have 3. So it just looks like that. And then now from there, we are told to find the derivative. It means the derivative of the dot product of P and the Q with respect to T. This equals to what? This is what now here is required. This is what is required. So the first thing that we are going to do, we are going to find the dot product. So dot product here, P dot Q equals to what? So we can use this column matrix T, then T square 2T. Now we dot with that 1 plus T square. Yes, T square. Then 2 minus T, and here 3. They appeared now. So dot product, it means now we find the product of this and then we plus. Then we get the sum. So we sum products of every unit coefficients for I, J, and K. So it means here we have something like T times this, we get T bracket 1 plus T square. Now we sum T square times this, we get that T square you times 2 minus T, then you sum 2T times 3, we get 6T. Yeah. So now the dot product of P and Q now, so becomes, so here will be T with plus T cubic, then again we plus 2T square, we minus T cubic, then we plus 6T. So from here we can just check the terms, the like terms, then we operate them. For example, here T cubic, we can operate. So this and that now will cancel out. And then now T cannot be added with 2T squared because they are not like terms. So here remains this one and that one, we get 7t, and then now 7t, then we plus the 2t squared, because this one and that one cancel out. So from there now this represents the dot product of vectors p and e and the q. Now if you find the derivative now, the derivative of the dot product with respect to t now, this becomes what? So this is just an expression of t. So it's like representing the power series. So here is a power function. So we just differentiate by the power rule of differentiation. So this becomes 7, then now becomes 4t. So up to there now, we have managed to find the derivative of the dot product of vectors p and q with respect to t. So this becomes that way. Now let's move and see part B. Now case B, in case B, we are given the velocity of a body at time t now, application part in vector analysis, is given by the vector v equals to of 3 dimension, I, j, and k. Now find the expression for the acceleration. Acceleration here, and the displacement, a vector of the body at time t. Given that, this displacement vector is known because t was 1. So t here provided t. When t is 1, it means the displacement vector, it looks like 3i minus j plus 2k. But now we are told to find this displacement expression in terms of vector. It means we are very fortunate. We are provided with the velocity. If that to be the case, it means now if we integrate velocity, because this velocity is the function of t, if we integrate with respect to t, we are going to get the displacement. And this now is provided because if we find the indefinite integral of that velocity function, it means we'll end up getting the constant. So that constant, I think, it will be calculated through this information that we are provided with, the displacement. Now, by starting here, we have two issues to deal with. The first thing here will be the acceleration and the displacement later. So we have two parts to work on. So starting with acceleration, now we can say given the velocity function, so the velocity function vector, it is 3t squared, now I, then we minus 2tj, then we plus 4k vector. So from there, if we need acceleration, we know from kinematic concept, we know acceleration solution. From the kinematics, we know acceleration equals to the derivative. If we differentiate velocity function, now we get the acceleration function with respect to t. So here with respect to t. So if we are going to differentiate velocity with respect to time, we are going to get acceleration expression. It's like saying acceleration equals to velocity. Now you divide by time taken, by the time taken. So from here, it's a matter of differentiating this velocity now. Then we end up getting the what? The expression for acceleration. So here will be, so we just differentiate this one. So it will be 60t, then I. Now we minus, here will be 2j. But here we don't have t. It means when we differentiate this, we consider it as constant. So now that's one become, it becomes 0. Becomes 0. And now acceleration expression becomes 60t I minus 2j. So that will be now the expression for the acceleration. Now, if that to be the case, then we ask again, we find the displacement. We find the displacement s of the body at time t. So if that to be the case, we need to go back to the velocity function, this one, if we try to integrate velocity, it means now we are going to get the displacement function. Now the concept comes because velocity equals to displacement over time. If you remember in kinematic concept, so if velocity is displacement over time, for we to get now displacement, it means we need to integrate what? Velocity. We need to integrate velocity because this here displacement is acting like the fundamental and the velocity is acting like the derived quantity. So for you to get the fundamental but through the derived quantity, it means you need to integrate. You need to integrate. So integration is very important now. So now we can say when now we integrate, then displacement function is a function of t is the result of integration of the velocity with respect to t, with respect to t. So if that to be the case, then now we can have this displacement function equals to the integral. So this becomes 3t squared. Then now we have I minus 2t, then j, now we plus 4k. So with respect to t. So from there now we're just integrating. We take integration inside. So here becomes, it becomes now integral of 3t square I with respect to t minus integral of 2t j with respect to t. Now we plus integral 4k now with respect to t. So it just becomes like that. So if that to be the case, now on taking integration here, so it's going to be this 3, we take it out. So now we'll have t cubic over 3 times I. Now we minus the 2 out. When integrating t now, it becomes t squared over 2. But remember here we have j, and here is I. And now we plus this 4k is constant. Then when integrating the t now we get t, then we plus that t constant because this is indefinite integral. Now from there, if we simplify, here 3 and 3 will cancel out. So we remain with t cubic, then vector I. 2 and 2 cancel out, we remain with t squared j, then now we plus 4k t, then we plus c. So if that to be the case now, this now will be the displacement function. But now we are told we have already provided with displacement function provided t is known, t is 1. So now we can use this approach so as to calculate the value of this c here, the constant of integration. So now we can say since t is 1, then the displacement function when t is 1 now becomes, remember that's a vector. So where t here, it means now we put t, we put 1. So that 1 cubic now will be 1 times I, so we get vector I. So we minus j, then there we'll plus c 4k. Then now we'll plus c. But displacement function when time is 1, we are provided here. So it is here. So this one now is substitute here. So we say then it will be 3i minus j, we plus 2k, then now equals to, we compare with that one, I minus j vector, we plus that 4k vector, then we plus c. So here now it will be simple to find the c. So it's a matter of collecting the like terms and operating them. So now when we take all this to this side, so c becomes what? So vector c becomes 3i minus I, we get 2i. Then negative j plus j, now it's cancel out, it'll be 0. So we say it'll be 0j. Then 2k minus 4k, we get minus 2k vector. Then now vector c, this constant c becomes, it is 2i, then we minus 2k. Now after having calculated the constant, we go back here to the displacement function, this one here. Then where k now, where c, we just add this 2i minus 2k. So then the displacement function, the displacement vector becomes, so it will be s of t equals to what? So that one will be t cubic I minus t square j, then we plus 4k vector, then now we plus c, it is 2i now, the c there, it is this one, now we minus 2k, this one. So now you collect the like terms. So when we collect the like terms here, I, this one and this one, so this becomes t cubic, it becomes t cubic, we plus 2 brackets, then vector I. Then again, j is only 1, t squared, then j, then k, there are 2 here. So 4k, this minus this, now we plus c. This becomes 2k vector. So now this now will be the displacement vector. Yeah, as a function of who? T, as a function of t, as actually from the question. So the expression for the acceleration now, it is 60 I minus 2j, and the now expression for the displacement of the body at time t, now it is given as that one. So up to that point, we have managed to answer part B. Now let's see part C. Now case C, here, we are told determine the area of the parallelogram ABCD with vertices A that's given in terms of 3-dimensional vector, and B, the point 4, 3, 1, these are positional vectors, and point C is 2, 2, 1, and D, it is 5, 7, negative 3. So all these vertices represent position vectors. It means that one for point A is like, say, vector OA from the origin. That for point B, the corner, the vertex B, now that will represent the vector OB. That's why we say they are positional vector. It means they originate from the origin of the XYZ plane. So from there, if you're looking now for the area of the parallelogram, it's a matter of understanding the adjacent side of this parallelogram and getting now the vectors which are found in those adjacent sides, where we can apply the cross product so as we can find that area of the parallelogram. So from there, how do we do it? We can say now solution. So from the adjacent sides, so here will be AB, and BC. So these will be the adjacent side of the parallelogram. As you know, parallelogram It just look like this way. I can see these are parallel sides. Yes. So if here is A, now B and C. So if we deal with these adjacent sides, A, B, and BC, and here it is D here. Yes. So we are able now to find the area of the parallelogram. So if we choose now AB and the BC to be the adjacent side, now we can end up getting the area of the parallelogram. So now, vector OA, this one, we are provided that is what? 1, 2, 1, -2, 3. And the OB, that is given as point B now, because this is a positional vector. They are started from the origin, which is 0, 0, 0, from the XYZ plane. And then now we have C, or C vector, that is the same as point C, 1. Yes. Now from that concept, we are able to find the vector AB as adjacent side, because, yeah, this one is adjacent side, because that one looks like displacement. These adjacent side are displacement, whereby we can find the length. As we know, length is magnitude in vector concept. So AB now, how do we find the vector AB as adjacent side? It means we take the position vector B, we minus the position vector A. So it's a matter of saying OB vector minus OA vector. And now from here, it's like taking this minus that one. So x val to x val, y to y, and z to z val. So 4 minus 1 here, now we get 3, 3 minus -2, that's become 5, positive 5, and the 1 minus 3, that becomes -2. So from there now we have vector AB. Again, we find this vector displacement vector BC. So it's a matter of saying OC minus OB. So if we subtract, we get that displacement from B to C, as the unit of length. But here now, C this one, B this one. So we take 2 minus 4, we get to -2. Then 2 minus 3, we get to -1. And now 1 minus 1, we get here 0. So now from there we have AB and the BC. Now area now of the parallelogram is given as the box product, the magnitude of the box product of AB vector and the AC vector. So that will be as the box product of the two adjacent vectors. So now let's see how we can do it. How do we calculate it? So area equals to magnitude, or the modulus of the box product. So this double stand means the absolute bracket that represents the magnitude. So we need to find first the box product, the inside manipulation, the AC, so to see what we get now. So here we apply the concept of determinant. Now we can just put I, J, and K. These are the dimensions of our vector, I, J, and K. Then now AB, we have 3, 5, and -2. So we just write here 3, 5, -2, and the that So that is AB and AC. So here we need to find also AC. Sorry. So here AC was very important. AC was very important. It means we take OC, we minus OA. So OC equals to what? So this one, so it is 2 now, minus 1, we get 1. Then 2 minus negative 2, we get 4. Then 1 minus 3, we get negative 2. So this will represent AC. And the formula says AB, we cross with AC. So this one has to be here. 1, 4, and here is negative 2. Yes. Yes. Up to that point now, we can undergo the determinant concept. So it's like we introduce that positive negative sign rule. The sign rule in determination of the determinant. So this is I. Yes. So now from there, this we take out that positive I. Then this cancel out. The first row in the first column cancel out. We remain with 5. Here is negative 2, 4, negative 2. Then now we take minus j vector. So here becomes cancel out and this cancel out. The first row cancel out and the column containing that j cancel out. So we remain with the element 3, negative 2, 1, and the negative 2. Then again, the positive k out. So the third column cancel out and the first row cancel out. So we only remain with these elements here that make a square matrix of 2 by 2. This one here. So from there now we can operate as usual when we are calculating determinant of 2 by 2 matrix. So what exactly do we get? It's I bracket. Negative 2 times this we get to negative 10. Now we minus this time this is negative 8. So it's a plus 8 here. Minus j vector. Then negative 2 times this one we get to negative 6 minus. This will be negative 2. Now we plus 2. Then now we plus k. So 3 times that we get 12 minus 1 times 5 is 5. So now operate. This and that we get negative 2. So we multiply with this, we get negative 2i. Then this and that we get negative 4 plus times that we get positive 4j vector. Then this will be 7. Now we plus 7k. So that now will be the cross product. Now we come to find area now of parallelogram, which is the modulus of the cross product, AC. So this becomes, so it's a matter of taking now the square root. That will be the square root of these values for x, y, and z, because this is 3-dimensional vector. So it is negative 2 square, we plus 4 square, we plus 7 square. So at the end of the day, we get negative 2 square. It is negative 2 times 2. That one becomes 4. Now we plus 16, we plus 49. Because this is 4 times 4 is 16, 7 times 7, it is 49. So now when we add here, this is 20. 20 plus 49, we get, it's a radical of 69. Then now this we say units, units, because unity, unit squared. The unity, unit squared. So it's the area. So up to that point, we can say now, this now will represent the area of the parallelogram, whereby it is obtained by the formula. We take the cross product of the adjacent sides that we saw is AB and the AC, and how to find it from the concept of positional vectors, whereby AB the same as B minus A. So for we to obtain the short distance or displacement along AB adjacent side is like taking the vector, position vector for B minus position vector for A. The same apply position vector for C minus position vector for A. Then now you come to find their cross product. After finding their cross product, you come to find the modulus or the magnitude. And from there now, we can have the area of the parallelogram. So up to that point, we are through with that question number 3 that appeared in Advanced Mathematics paper 2 in the year 2025. Thank you.